Okay, doors are closed. I think we can start. Can everybody hear me? If I'm not sure how loud this actually is. It sounds loud. Very good. Cool. Thanks everyone for coming in on a Sunday morning. That's really cool. Really appreciate it. Good to see a bunch of friends in here, and everyone else obviously too. If I sound a little funny, this might be a German accent or the karaoke party last night, which was a lot of fun. I hope you all made it there. I'm going to talk today about DFIR and IDS for Wi-Fi networks. So DFIR, Digital Forensics and Incident Response, and IDS, Intrusion Detection. This is the first time I'm talking about a Wi-Fi topic. I spent a lot of time working on this, and I spent a lot of time in the whole Wi-Fi space in this summer. I think it's the spirit of this conference too, that I would love to get your feedback, not only on the talk itself, but also on everything that you're seeing, because I think we're all coming here to discuss things. So, because I'm showing this for the first time to such a broad audience, and I'm also releasing an open source tool today, I would love to get your very honest feedback after this, because, as I said, I'm also still kind of new to the Wi-Fi space, so you might have a lot of input. So I'm leaving a lot of space for Q&A today. And yeah, I hope we'll have a discussion either during the talk. I'll be around until tomorrow afternoon. I hear there's some kind of beer fest today in town, so I guess there's a lot of opportunity to to talk for the rest of the day. A few things about me. My name is Lennart Koopmann, 29 years old. Before I kind of stumbled into the security space, I was a software architect and software developer. I started the Greylog open source project in 2009. I don't know if any one of you heard about that before. It's a log management tool, open source, specifically or very much focused on security and very much built for logs. So I guess you all would like that. This talk today, however, is not about Greylog. I'll use it because I'm obviously very familiar with the tool, and because this other open source thing that I'm releasing today is actually writing into Greylog, but you could use any other log management tool for this probably too. So I don't want to make this an awkward vendor talk or something. I was born and raised in Germany, moved to the US in 2015, and if you want to follow me on Twitter, this is where I spend a lot of time over the day. You can do that. It's @ then my first name, or you can also subscribe to my blog, which is at wtf.horse, which was the best drunk domain purchase of my life, I think. It's a premium domain. They charge you like $90 for that. So it was still a good idea, I think. And you always have to put an HTTPS in front because no one will know that this is an internet address. But not the smartest marketing idea, probably. So I moved from up there on the right in northern Germany, where it's very cold and never warm and never really cold, so you only got kind of the autumn vibe all day long, to Houston, where it's very wet this summer especially, and also very humid. So I moved from this place to this place. No, it's actually pretty beautiful. I love Houston. You should all come. Okay, the agenda for today. I want to give you a really, really short intro to Wi-Fi security in general, and then spend a little time looking at the 802.11 specification and protocol, and specifically what management frames are, because that is important for the whole, not only IDS, but also the DFIR part for Wi-Fis. I want to explain a few of the common attacks. So you probably all heard about, for example, rogue access points, evil twin attacks. So I want to show you some of those and also explain how you can detect those. So for example, there is a very good open source Wi-Fi intrusion detection tool called Kismet. So if you look at their code, for example, you can actually see how they detect certain stuff. They have pretty good documentation explaining all of this. So I want to go over a few of these things. Then I want to show you my new tool, which I called Enzyme. I had a very good discussion last year with people in New York City who run kind of a lab co-working space, which is interesting. They're all in biology and DNA and stuff like that. And we were talking about is there any similarities between cybersecurity or information security and how the human body works and how the human body reacts if it finds viruses or bacteria, for example. So somehow I ended up with the name Enzyme. This is an open source tool. I'm going to talk more about this. And then give you actually a few examples. This is going to be a live demo, so let's hope this actually works. If it doesn't, I have some screenshots prepared, because I did live demos before and sometimes they simply don't work. So we have a fallback for that. And then, like I said, we have a lot of time for Q&A today, because I would anticipate that there's going to be a bunch of questions. I would really love that. So, short introduction to Wi-Fi security. I always knew before I spent more time with this that it's probably kind of insecure to be in a Wi-Fi in general. It is a total mess. The more time you spend with it, it's just you want to put wires in your house everywhere and just rip the card out of your MacBook. Attacks are pretty hard to detect and also very hard to mitigate, simply because the attacker could be sitting in the parking lot. So it's something that gets directly into your local network, but still you can be far away, so this doesn't have to be someone who has a network cable with them and just plugs it in the wall somewhere. It could be sitting in the parking lot and attacking your network. And another problem is that Wi-Fi today is extremely popular. I mean, light bulbs have Wi-Fi today. Every phone has Wi-Fi. Every computer has Wi-Fi. My mom uses Wi-Fi and just thinks that's the internet. This is how consumers think about that, right? And that's okay. But the problem is they don't understand the risks and the attack surface of this. So attacking is also very cheap, and I would say it's commoditized by now. Probably a bunch of people walking around here with little Wi-Fi pineapples that make attacking a Wi-Fi so easy if you understand a little bit about it. This is actually how I got into it, because everyone had one, so I thought I'm going to buy one and just look at it and got interested in it. And it's just so easy and it's so cheap. I mean, you get what does a Wi-Fi pineapple nano cost today? Like $100 or something off the internet. You have it 2 days later. So it's really easy to attack and it's really cheap to attack. Yeah, this is, I mean, they sell them with these little tactical packs, and you can just strap them on your belt and walk around with it. This is the Wi-Fi Pineapple. It's basically a complete attack platform that has multiple Wi-Fi chips in it. Comes with a nice little web interface that you can open on your phone, has a management access point, and you can just click around a little and you'll start certain Wi-Fi attacks. That one really opened my eyes. So, the Wi-Fi standard is 802.11. I learned that it's abbreviated as just .11. That helps. There's 17 different versions. So you'll probably see when you buy a Wi-Fi adapter online, you'll see that it's an 802.11a, B, G, N. What I learned is, and that's actually different, that's very important, the different versions don't actually define big differences in the standard itself. This is mostly about different frequencies, bandwidth, modulation, and by that data rates. So one of them, for example, open up the 5 gigahertz license-free frequencies. So 802.11 is usually 802.11. It doesn't really matter what kind of letter is behind it. So that makes it easier already. So we can just talk about 802.11 in general. That protocol is also defining frequencies and channels, because whoever wrote this figured out pretty early, oh, there's probably a lot of people are going to use this, so we have to spread this out over multiple channels and multiple frequencies. So for the 2.4 gigahertz band, for example, this is channel 1 to 14, where I think in North America it's really only channel 1 to 11, where the most popular channels are 1, 6, and 11, because they don't overlap with any other frequency. So if you have a corporate network, so our office, for example, is in downtown Houston, where there's just a lot of noise. We have these weird antennas on the roof that mess with the network in itself already. You can see that there's a lot of noise on that frequency band already, so they come up with new and new frequencies to make more room for all the communication. Now that light bulbs and toasters and juice makers need these frequencies, you just need more frequencies, basically. And the MAC layer of the 802.11 standard defines 3 types of frames. A frame, I'm not following the terminology of 802.11 here very strictly, simply because they talk about stations and non-stations and all kinds of stuff. I simplify this a little. The standard itself is this thick. It's a lot of stuff in there for a bunch of functionality I've never seen before in any kind of Wi-Fi. But I'm going over the most important here. So there's 3 types of frames. There's management frames. This is what we'll be focusing on today. There's control frames. This is simply to assist in delivery with data frames, which is your actual data. So in your data frames, your emails, your websites, HTTP, TCP, everything is in those. However, to be able to join a Wi-Fi network, you have to do a whole dance with a bunch of management frames. This is if your computer or your phone decides to connect to a Wi-Fi network, then it's sending a bunch of management frames back and forth until it's authenticated and then able to send control and data frames. Control and data frames are interesting if you want to sniff data. We're not really focusing on that today. We're focusing about the attack surface of management frames. So every type, so every frame type, then defines several subtypes. And I learned that the most important thing to understand if you want to learn more about Wi-Fi security is to understand the subtypes of the management frame type. So there is a bunch of them. We're going to go over them right now because this is really important for the IDS and the DFIR part. So the first frame type is called the authentication frame type. I put the abbreviation behind it. That's kind of a standard. It depends on what you look at. If you are, for example, if you're analyzing stuff with Wireshark, it might be a little different. I follow those of TCP-DUM and the official standard. So you'll see these abbreviations later in the demo a little more. The authentication frame is what your device sends as a first step when it wants to join a wireless network. So you're at Starbucks, you want to join their network, it sends an authentication frame, and being authenticated or not restricts the ability to send or to receive in a network. Again, you have to be authenticated to be able to send or receive any control or data frames. If you're not authenticated, then that stuff's simply going to be discarded. No one's going to look at it because you're not in the association table of the access point. The authentication process itself, and this is already where the standard gets a little interesting, I would say. It depends if you're connecting to a WEP or, for example, a WPA network, simply because it feels like the WPA encryption has kind of been bolted on the original 802.11 standard when everyone figured out, oh God, WEP is not at all secure. So if you see a WEP network somewhere, just do not use it. You can crack those so fast. I hope that's common knowledge by now. But this is different. I don't want to go too deep into that, but there's a different sequence of authentication and secrets and stuff being exchanged before you're authenticated. Then this is probably everyone's favorite frame. It's the deauthentication frame. You'll see that a lot either in an attack itself, and we're going to look at that in a second, or you'll see that as part of another attack. What this does, it's a simple unidirectional announcement from one station to another station. So for example, from the Hyatt access point to my iPhone, saying, hello, I would like to wish to terminate any secure communication with you. For whatever reason. This is unidirectional. They immediately take you out of the association table. They act like you're not in here anymore, and your phone then has to decide if that should be followed or not. Usually your phone will do that. Any device will do that. And basically, the access point just tells your phone to go away. I don't want you here anymore. The problem is management frames are completely unencrypted and can be spoofed very, very easily. It's completely unencrypted frames, so if you have a Wi-Fi card that allows you to send any kind of packet, which is any card that supports packet injection, which you get for like $30 off of Amazon Prime, so if you order them now, you'll have them probably by tomorrow morning. That means that I could have a Raspberry Pi here that just sends a deauthentication frame, and your phone would follow it if I just pretend that the access point sent it. And that's just a field in the message. It's not encrypted. Everyone can send that. Now, when I read this for the first time, I thought, well, to put this in the standard, that doesn't sound like a very good idea. But if you think about it, you actually need something like this, because it comes with a reason code, and there's, I think, 70 reason codes that are defined, and another, I think, at least 200 that are open for vendors to use. But a reason code could be, for example, your previous authentication is no longer valid. This is what happens when Hyatt decides you get the guest access for 6 hours, and then some cronjock kicks you out and says, nope, deauthenticated, you have to buy our pass now. A station has to be able to kick you out. The problem is that everything's unencrypted, and this, I think, was simply done to make it easy for consumers to connect to networks. Because if you had to exchange kind of a, because remember, the management frames are used to connect to the network at all, so there's no authentication yet at this point, so you would have to kind of exchange a pre-shared key and all of that. This would never work, especially not with a juice maker, I guess. So This is simply a fact, and this opens a huge attack surface. More about that in a second. Then there's the association request. This is the last step for joining a network. This is basically after you're authenticated, you say, okay, I would like to be associated with this access point now. Because you also have to remember there could be, like here in the Hyatt Wi-Fi, for example, there's probably 100 access points that serve the same network. So your phone decides which access point to actually connect to. This then allocates resources on the access point, synchronizes both stations. This is just part of the authentication, basically. It's the association response. This is simply the access point says, yep, you're allowed, I got you in my association table, all good. This also includes information about the supported data rates, because many chips today support a lot of different data rates. They could be on different data rates and different channels. All of this is done during the association request. So they basically agree on a format of communication when that happens. It's the reassociation request. This is when you walk down the hallway, your phone decides, wait, I'm much closer to this access point now. I should de-authenticate or should disassociate from this one behind me that has a lower signal strength and reassociate to that one. Then these two will talk to each other and be like, no, he's authenticated here already, so I'll let him in here. All of this happens. This is a reassociation request. I don't see them very often. I honestly don't know why, but they are there apparently. Same thing with the response. This is just the same thing where it says like, yep, you're in, you're authenticated, and you are associated with me now. This disassociation, this is when my phone says, nope, I don't want to be associated with you anymore. This is basically like a graceful shutdown. Imagine if you would just walk away without disassociating, then the access point would have to wait for a timeout to actually clear you out of the association table, because you might still be there, but they'll wait a few minutes and then be like, nah, he's probably gone. I'll kick you out. So this is just a nice way to do it. The standard says you should do it. But if you just walk away, it obviously doesn't happen. You just poof, go away. This one is interesting. This is the beacon frame. The beacon frame is by far the most common frame type that's in the air here right now. This is access points basically announcing that they are there. They are like a beacon out there, and they say, hello, I'm here. This is my supported rates. This is the channel I'm operating on. This is my SSID. If you want to connect to me, I'm here. This is, if you click on your, on Windows, I think it's on the bottom right, on OS X is on the top right. If you click on your little Wi-Fi icon, it shows you all the networks that are there. It says I'm scanning for networks. It's not actually scanning for anything. It's just waiting for beacon frames on all channels to come in. And then it just collects the SSIDs and tells you this is all of the access points that are in range. So it's really like the name. It is a beacon of access points that are out there. Then there's the probe request. That one has a lot of very interesting information. So the phones that are in this room here right now, if you have Wi-Fi enabled, they're probably sending tons of probe requests in this moment. This is basically, this is your phone asking the whole vicinity around you, is a specific access point here, and it will answer with a probe response, which comes in a second. So if you're, for example, you're leaving your office, you're going home, then between that, you're in your car, you're in the train, whatever. Between that, your phone is probably not being connected to Wi-Fi. So it constantly tries to figure out, wait a second, maybe I'm close to home, so let me ask if I'm close to home. So it sends out a probe request that says, hello, home network, are you here? And then it listens for a probe response from the home network that says, yes, I am here. That is interesting because it's unencrypted. You can listen to all of that, and you can build pretty interesting profiles of the phones that are around you, because they'll show you your office network. In fact, my phone is sending this for our office network in Hamburg, where all of our engineers work, and for my home network in Hamburg, and for my home network in Houston, and for our office network in Houston. So you can build pretty interesting patterns, especially with these databases online, where you just enter an SSID and it shows you where this SSID has been seen. So there's stores now out there apparently that are using probe requests to identify phones in their stores to see how people are moving around. Because if you put enough sensors around that just read these probe requests, then you know, oh, this person that is constantly asking for this network was here on Saturday the last time, spent a lot of time at the milk aisle and is now at the egg aisle, for example. You could do that if you have 3 sensors. You can triangulate where these things are coming from. So your phones are doing that in this moment. It's a probe response. This is just an access point saying, yep, you asked for me, I'm here. So now there's common attacks, obviously. The most common one, and this is, I guess, what a lot of people played around with at least, is sniffing traffic from open or even encrypted networks. So if you are around an open network, like here I think the Hyatt network, you can go in and you can just sniff the traffic that's going on. So whenever you're on a Wi-Fi, you really either want to put a VPN over this, one that you trust obviously, or you want to make sure that everything you do is going through encrypted channels, so HTTPS. You should do that anyways, but just as a reminder, all of this stuff, this is not at all secured in any way if you're connected to an open network. It's really easy to read. I remember that a few years ago, someone came out with this Firefox extension, I think, or some kind of little tool that would just listen for the network traffic at an open Starbucks Wi-Fi, for example, or any other coffee shop, and then just give you Facebook logins. It would just show it to you. And this is, when this came out, people really started to enforce HTTPS. They came out with HSTS, all of these things to force people to use encrypted communication on a Wi-Fi simply because it's so unsecure. Now, what many people don't know is that they think, well, I mean, an encrypted network might be a WPA2 pre-shared key network. The problem is that this can also be sniffed if you are in the network. So if you know the network's password, so you're in your office network, and obviously because you're an employee, you know the office network's password, then the connection between you and the access point is encrypted in a way that has been negotiated between you and the access point. So you have your own encrypted channel between these two stations. The problem is that if you sniff the authentication process, you get the whole key, so you can decrypt it again. So if you have the master key, which is the password you enter when you connect to the Wi-Fi, you can read the traffic of anyone else who's in the Wi-Fi too. There are certain attempts to block this now. There's all kinds of enterprise encryption stuff, but really most of the things you see out there, I guess, is WPA2 with a pre-shared key. Remember that if anyone else has the master password, very easy. There's a bunch of tools out there that will do that for you to still read the communication of everyone else who's in that network. So that doesn't make that does not give you security at all. So when you're in a Wi-Fi, always put this through a VPN or make very sure that you have encrypted channels. And there's some things out there that you just forget. For example, Git. If you use Git, that is usually unsecured. So if you don't use Git on GitHub through HTTPS, that can very easily be unencrypted. So there's all kinds of stuff you want to think about, and maybe just tunnel it through a VPN that you trust, which is a whole other talk, I guess. This attack, so sniffing traffic, pretty much impossible to detect because the way you do it is you just passively sniff the traffic, and then you analyze the captured traffic, and you just decrypt it. So it's basically impossible to detect because it's in the air anyways. You just have an antenna that picks it up, and then you decrypt it offline. Another common attack is jamming. This is something that some people like to do at conferences for some weird reason I don't understand. But you can either do classic jamming, like just put garbage over the frequencies so nothing in the vicinity works on that frequency anymore, but that needs pretty special equipment. I think that also gets certain authorities pretty close to you pretty fast. The thing is, however, you can do that on a higher level of the protocol, which is the authentication frames. There's little Arduino firmwares, for example, or Raspberry Pi Zero firmwares that will simply listen for all the MAC addresses that are connected to an access point, and will just blindly fire the authentication frames around, so all these devices constantly disconnect. That works on tiny hardware. You just need an antenna. That's pretty much it if it has a Wi-Fi chip and it allows packet injection. This can, however, be detected by simply counting the number of deauthentication frames. If you have a histogram of how many deauthentication frames are in the air, you should be able to count that and find anomalies there. I'm going to show that in just a second. Then, this is, I guess, the most interesting one at least. This is rogue access points. So, what would stop me or anyone from just spinning up an access point, calls itself Hyatt Wi-Fi, you'll probably join it. If it's the closest to your phone or your phone or your device might actually pick it automatically because they tend to connect to the strongest signal strength. Now I got a man in the middle pretty much because everything goes through my device, and I can do DNS poisoning, ARP poisoning. I can listen to all the traffic very easily. In fact, I don't even need to mess with all the stuff because it goes through my device anyways. So this is, I think this is the most severe attack that's out there, and this is also the most, I would say, popular attack during pen tests and any kind of red teaming. Because simply it's so easy to trick devices to connect to something, because if you can spoof everything, you could even give it the same MAC address as the other thing. Who would know that this is a rogue access point and not a normal access point? There are, however, several ways to detect them, luckily. This is what Kismet is extremely good at. You'll be able to do the same thing with Enzyme and with Greylock, or you could just use the combination to respond to alerts that Kismet already gives you. It's up to you. So you can detect a rogue access point in several ways. You could, for example, do BSSID whitelisting. This is basically the MAC address of the access point, and you can say, my office has 25 MAC access points. That's 25 MAC addresses. Whenever I see a beacon or probe response or anything that advertises my SSID out there that has a different MAC address, then all alarms should go off, because that probably means that someone runs a not very sophisticated attack with simply just another access point that has the same SSID. Problem is, you can simply spoof that. You just walk around, record the MAC addresses of the existing access points, and just put that MAC address into your access point. Now it's really hard to detect it again, right? So this only protects you from very, very unsophisticated attacks. The good thing is, there's other ways to detect it. A very interesting thing, I thought, is by detecting non-synchronized MAC timestamps. A MAC timestamp is a timestamp that is included in every beacon frame of a access point. So remember, this is the access point sending dozens of these every second, saying, I'm here, I'm here, I'm here. The other access points will listen to that, and they actually use these to synchronize each other. So because it's extremely important that all of the access points are synchronized up to, I think, I might be wrong, 25 microseconds or something. They have basically their own little version of NTP that goes directly over the air, and they synchronize each other through a timestamp that they broadcast in these beacons. And the thing is that a lot of people who will be a little more sophisticated and at least spoof a MAC address and run what's called an evil twin attack, they will probably not bother to synchronize these MAC timestamps. So you will have, you could analyze the MAC timestamp, and because it only increases, it's just a long that gets that increases and increases and increases. You will have steps in there in every beacon that comes from the wrong access point. So if you collect all of these beacons, and this is something that Enzyme is doing, then you can basically draw a chart over the value of the MAC timestamp that's in the air, and that should just go linearly go up. If that thing does something funky, that means there's probably someone around here who spoofs an access point without synchronizing the MAC timestamp. You can also detect unusual channel or frequency usage. So if your corporate network always runs on channel 11, suddenly appears on channel 2, might be something interesting. The problem is, to avoid contention and bandwidth issues, a lot of the vendors for the better access points are dynamically choosing the frequencies and channels now. So my home network, for example, is already jumping from channel 1 to 11 because my neighbors are already on channel 11, and when they get very active, then my access point switches to something else. So that doesn't really work anymore. It's also, this is the easiest to spoof probably. You just run your access point on the frequency that the others run on. Now you wouldn't be able to be detected anymore. A crypto drop could be that your network is usually WPA secured, and suddenly there's an access point that is not. That could also just be a very unsophisticated attacker. That will be something interesting to see. And then something else that I thought was very interesting is by analyzing the signal strength. If you look at, now imagine someone is spoofing the MAC address of an access point. An access point doesn't really move, right? It's mounted to the wall, it's sitting somewhere. If you draw a chart over these over the mean signal strength for every MAC address out there, if suddenly there's outliers in there again, if this thing starts to get a little funky, that probably means that someone with the same MAC address sits out there in the parking lot, or sits somewhere where the access point usually is not at, and you have a completely different signal strength. So this is another way to figure this out. The problem is that there's tools like Kismet, and they're great for detecting this kind of stuff. I really like that project. They also do a lot of Bluetooth stuff now. A lot of fun, open source. Should definitely try it out. The problem is that you just get an alert, and it's really hard to respond to that alert, right? I mean, imagine you get an alert, hey, there's a rogue access point. So what you gonna do now? Shut down, pull the fire alarm? I mean, what you gonna do, right? So it would be great, I think, or you couldn't, I mean, the answer would be, okay, there was a targeted rogue access point attack. That wasn't just some kid walking around with a pineapple that just sends DFIR frames all around. It was a targeted attack, someone tried to get in here. But I have no idea how to find out who connected to it. I want to find out who of my employees connected to that thing, right? That'd be great. I don't know for how long it was there necessarily, and I don't know where it was located physically. So basically, you just get very nervous, but you can't do that much about it. So Wireshark and TCP dump can collect all these frames. It's actually pretty easy. You just select the interface. You just select the interface of your Wi-Fi adapter in monitor mode, and it will just spit out all the 802.11 frames. It's very easy. The problem is that they really fall short on long-term collection and analysis. You'll probably run that for an hour, maybe a few minutes. Then you put it in Wireshark. You follow the little loading, this famous loading indicator on the bottom. It takes forever. Your computer starts to lock up. They're great, but they are not really there for long-term analysis. You wouldn't want to analyze 500 million frames out there with these tools. So that's where I stopped with my experience with Wi-Fi security, and took a step back and thought about, wait a second, I know about this tool that allows you to collect a lot of structured data and allows you to analyze it. Because if you think about it, really 802.11 frames, especially the management frames, that's kind of like a net flow stuff that comes from your router. Very high level information about what happened with a lot of meta information about who communicated with whom in what way, right? So I thought, wait, we have something like that. It's called Greylog. I'm kind of familiar with it. So I was on a vacation in Europe. I got bored after a few days, and I started writing something that reads these frames off the air, structures them, and writes them into a Greylog. And that's what I called Enzyme. Enzyme, together with Greylog, allows you to store this data for a very, very, very long time. I'm running it in my home lab with 2 Wi-Fi adapters that are hopping through all channels of the 2.4 and 5 gigahertz range. It's been running extremely stable. It runs on a Raspberry Pi. I'm running one in our office, actually, that's downtown Houston, on like 24th floor or something. That gets a lot of frames. That's on one Raspberry Pi 3 Model B, and it's probably a 25 to 30% CPU usage. So it's pretty fast, even though it's written in Java, which I'm just very familiar with. But you only run it on the sensor. You don't have to install any client. So Java's actually pretty cool. That's going to be another talk. And obviously, I made it open source. I think there might even be a red team use for it. I would love to hear your ideas. If that is something where you just walk around with that thing, use it kind of like a pineapple, but instead of the pineapple kind of little clumsy way of analyzing the logs, you have that directly in a tool like Greylog, where you can, after that, do a lot of very efficient recon maybe. I don't know. I have no clue about a red team. I saw this talk before here. I did not know what's going on. More on the blue team side, definitely. So it's open source, obviously. This is what it looks like. This is 3 of the stuff you see there in front is the network adapters. Then I'm running this there on a different machine. It's like you get them, it's like an Intel Atom chip, I think. They're a little faster. They simply allow you to draw more power from it. Raspberries start to kind of randomly shut down if you put more than 2 of these adapters on it. So I wanted to have 3, put a different machine on it, but the real one really runs on a Raspberry Pi. That's what it looks like. It really only needs 1 or more Wi-Fi adapters that support monitor mode. It runs on OS X for if you just want to quickly test it. And the reference kind of platform is a Raspberry Pi 3 because that's what I run it on. That's where you find it. I have not bought a domain yet because you know what happens when I buy domains. In fact, last night I was about to buy one and I luckily didn't because the karaoke party. So find it on GitHub. Maybe if people like it, I might put a domain in front of it. We'll see. This is just github.com, my full name /enzyme. If you follow me on Twitter, I'm going to post a link to that. There's actually 1 or 2 in there already. Or you go to wtf.horse, that has a link to that too. Hope that's easier to remember. Okay, so I would say I try to make the live demo gods happy and just try to show you what this looks like. This is a preloaded page. I don't know if it will reload. Oh, before we start, let's actually go to Enzyme here. I was late to the party last night because I finished the documentation and the README. So this has quite a lot of README. You should be able to just download it and start it. This should have everything in there. If you get stuck anywhere, please open an issue. You're literally the first people that see this, so maybe this doesn't make any sense, or maybe it's just really hard to install. Just know already it's Java. So all you need is, Raspberry Pi, you need a wireless network interface that supports monitor mode. I'm linking to those that I'm playing around with. Actually, you get them one for 30, one for 40 bucks off of Amazon. You probably have some lying around already. This is all abstracted on the operating system layer, so I don't care what you run it with. If it supports monitor mode, we'll be fine. You see here, the other thing that it needs is a Greylock cluster, obviously. This is just one machine running on an old HP server somewhere. You can, if you want to play around with it, if you haven't used it before, if you don't have a Greylock running, there's operating system packages for everything. There's an Amazon image, there's an OVA if you just want to spin it up quickly on a virtual machine. This shouldn't be the hard part. If you like it, you can still build a real cluster, but this shouldn't be the hard part, I think. So, let me show you what the data looks like. Oh my god, it's working. It's amazing. Okay, so this is also coming through. It's a long. No, I'm going to skip that. It works. That's great. You see here, it's very familiar to. I think the usage of Greylock is very familiar to another log management tool out there that tends to be a little expensive at times. This is, by the way, if you go to GitHub, download Enzyme, you get all this data. If you go to GitHub, download Greylock, you get this thing. So it's all open source. Basically, you got your search bar up here, you got your messages up here, and you see, and I hope you can read that. For example, you see here that I received a beacon frame for the SSID Xfinity Wi-Fi on this frequency that equals channel 11. It's not WEP. It tells you which enzyme sensor got it. It gives you signal quality, signal strength. It tells you the SSID, the subtype, very important, and it tells you who sent it. So this basically tells me there is an access point with this MAC address, and it sent a beacon for this SSID. Now Greylock, like any other tool, allows you to, for example, say I want to search in the last 2 days. It's still working. You see here, this is how many frames came in. You see that in the last 2 days, I collected about 5 million management frames. Result came back in about 376 milliseconds. And now I could go in and say, show me the distribution of the field subtype. Some would call it a pivot table. We call it quick values. Click on it. Takes a little because of the story of the connection. I'm going to tell you later maybe. But you see that we get 75.53% of beacon frames, bunch of probe requests, bunch of probe responses, and some deauth frames. In fact, I think there is a neighbor who has a Raspberry Pi. If I show you this, so let's say I want to see all deauth frames of the last 2 days. Okay? Click on this button to say add to search query. I could also just type this in here and say subtype equals blah, blah, blah. But I just click on it to execute the search. I search for it. Now you see this is the distribution of deauth frames somewhere in North Houston over the last 2 days. You see we got a little spike here. So let's zoom into that. You see that this fills out a query for the time range that I just selected. I execute this thing. And you see that we got about 376 deauth frames here at 6:55 on Friday. And you see here, it tells me this transmitter tried to deauthenticate this station from this access point. It says unknown reason with a really weird code here. That is simply because I wrote the code wrong. This is not an attack. this is an issue already. This would give you a reason like the access point is leaving the station or your authentication expired, something like that. I just have to fix that. It's weird network protocols with short and byte order, and I got that wrong. Yeah, you see here. So now I might be interested in, say, this transmitter is deauthenticating stuff. So let's take the MAC address of the transmitter. I just copied that. Say again, I want to search in the last 2 days. And I'm just going to run a full text search for this MAC address and say, show me everything that this MAC address did in the last 2 days. Here we go. So let's see what kind of frames this MAC address sent in the last 2 days. Okay, it sent a lot of beacons and then about 82 deauth frames. That's interesting. So let's say, show me everything from this MAC address that has the subtype beacon so I can see what kind of network is this device advertising, right? Now we got all the beacon frames. And it is mostly broadcast beacons, which is interesting. So let's go back and see if we find another device in here. Just 1 second. This is not what I wanted. Here we go. Live demo, don't disappoint me. Here we go. So let's take, what do we have here? Let's say we want to instead look at the destination, like what was deauthenticated, right? So I do the same thing. Go into the last 2 days. Enter this. Here we go. This is the activity of this. Okay, now that's even more interesting. So again, go into the subtypes. And you see, it sent deauth, it sent a bunch of probe responses, and it sent a bunch of probe requests. So let's see what networks this device asked for. And you'll see it's looking for a network called AT&T Wi-Fi. So you can now, with this kind of stuff, if you detected that there was a rogue access point, you could go in and say, show me all the authentication frames that went to this device, and run a pivot table over the transmitters of that, which is the devices that try to connect. Do that, and then you'll get a list of all the MAC addresses that connected to this very specific access point. That might be a rogue access point. You can use the generate chart feature here to build this linear chart of the MAC timestamp, for example. You could use that to build the average signal quality of all of your access points that are out there. I am also using the lookup tables that are in Greylock that can be filled from any kind of API to, for example, get me a transmitter name, where I basically translate MAC addresses to known devices. So you see that this is my main access point at home. This is my extender at home. I don't know who Jane is, to be honest, but Jane's MacBook apparently sent a bunch of stuff. It's my Amazon Echo in the office. There's a Chromecast in the bedroom. So to make it easier to analyze all of this stuff, you can use the lookup tables to translate MAC addresses to names, for example. Now my favorite thing before we go, because we only got a few minutes left, I promised you more Q&A time, I'm sorry. My favorite thing is to go in and say, show me all the probe requests, which is in the last 2 days, that was about 296,000. Show me all the probe requests. And then give me the SSIDs that the devices asked for. There you go. This is my Sonos at home. This is going crazy a little. I don't know why, but you'll see there's a bunch of people asking for, this is AT&T networks. This, in fact, this is our network in Hamburg. That is about 8,500 kilometers away, but my phone asks for it. So this appears somewhere in North Houston now. You see everything here. The neighbor's car will appear in there. You can, with this stuff, if you wanted to, I'm very specifically not doing that, but if you wanted to, you could build patterns of when the neighbor goes to his car, if it's his wife or him, when the car leaves and when they come back, simply because the stupid Camaro is sending beacon frames that you can follow. You can even see how fast they drive away based on the signal strength. It's like, so This Wi-Fi stuff is crazy. It's a lot of fun to just send it in and just dig through it. So yeah, I open sourced this. I hope it's any value for anyone. And if you have any questions, you can fire out GitHub issues. You can connect me, follow me on Twitter. I'm around for the whole day until tomorrow night, actually. So if you run into me, I'm happy to talk about it. And I hope this was interesting. First time I did it, so thank you very much. I think we've got 5 minutes left for questions, so if there's any questions out there. Yeah? Yeah. Yeah, so the question was, is there any way to configure these channel hopping frequencies, for example? Yes, you can do that. Here's an example config, in fact. You see here that it has a channel hop interval. That's simply, it's currently in seconds. I might expect that some people want to have that in milliseconds, for example. I can change that. It also has a beacon frame sampling rate. So if you say, I only want to record every 5th, every 20th beacon, simply because it's so much data, then you can do that too. That's an interesting idea. That's currently doesn't do that. If you could open an issue for that, that'd be great. That'd be interesting. If you can send data back to Enzyme to look at something very specifically, because right now you do channel hopping. I mean, basically, you all saw the famous Wi-Fi cactus, I think, with this guy with like hundreds of access points, hundreds of Wi-Fi cards on his back. This is because if you do channel hopping, because the Wi-Fi card always has to be tuned to one frequency. If you want to get all frequencies, you have to hop over these frequencies. If you want to narrow into a certain frequency in a certain device, for example, I think that was your question, right? Oh, okay. Even better. Yeah. Okay, sorry, then I misunderstood your question. The question then was, can Enzyme, when I detect a rogue access point, and this means you understand the whole topic, can Enzyme then fire DAuth frames at the devices that are currently connected to it, right? To force them off the rogue access point. It currently can't do that, but that'd be interesting. Greylog has REST APIs, so you could have a Python script or something that just reads that from Greylog and then fires it off. That might be interesting. It's a very good question. Yeah. It currently only supports Greylog, but it sends a Gelf message, which is a Greylog message. Logstash, for example, supports that as an input. So if you want to write it somewhere else, sure. Mm-hmm. Thank you. Mm-hmm. Okay. Mm-hmm. Yep. Cool. Sounds good. By the way, if anyone finds a shop where you can get a Yagi antenna with a real, I forgot the name already, SPSMA something thing that works with a normal adapter, let me know. I still don't have one. For 3 months and a lot of different adapters,